So let's look one more time at determining the rate law for a reaction that has a two-step mechanism where the first step is fast and it has an equilibrium, and the second step is slow. So when we write our rate laws, the rate is going to be dependent on the slow step. So for this type of problem where we have a fast initial step, we are going to need to use that piece of information, because if we write the rate law based only on the slow step, we would get rate equals K, and we're going to call this K2, times the concentration of B times the concentration of M. And remember, for reactions, chemical equations that show up in a reaction mechanism, these are referred to as elementary reactions. And from an elementary reaction, you can obtain a rate law using the stoichiometry. But when we look at the rate law for this slow step, what we find is that we actually have an intermediate that shows up in the rate law. And we can't have intermediates in the rate law. So we need to be able to write a rate law that doesn't have an intermediate. What we do know from the first step, the fast equilibrium step, is that the forward rate is equal to the reverse rate. And this is the definition of dynamic equilibrium. And so if we write this out, the rate in the forward direction, we're going to give that a rate constant K1. Rate is equal to K1 times the concentration of A, and that's squared because we have A plus A on the reactant side. For the reverse reaction, we're going to give this a rate constant, K minus 1. So we'll have rate equals K minus 1 times the concentration of M. Now, because we have dynamic equilibrium, these rates are equal. So we can set the right-hand side of these equations equal to each other, which means we'll have K1 times the concentration of A squared equals K minus 1 times the concentration of M. Now, our goal here is to write an equation from this first equilibrium step that solves for M, so we can use that and plug it into our rate law based on the second slow step, because we want to get rid of the intermediate M in that rate law. So if we rearrange this equation, we're going to end up with the concentration of M equals K1 over K minus 1 times the concentration of A squared. And now we can plug this into the slow step rate law. Okay, so we can plug that into the rate law for the slow step. So then we'll have, from here, combining these, rate equals K2 times K1 over K minus 1 times the concentration of A squared times the concentration of B. So what I've done is I've taken this equation for M, plugged that into here for M, and I obtained this equation. Now, often what we'll do, because we're just multiplying rate constants together, we can say that K2 times K1 over K minus 1 is equal to a new rate constant. And often we don't give it a subscript, we'll just call it K. So when we write the rate law, we'll say rate equals K times A squared times B. And so that is how we write, or we obtain the rate law for a reaction mechanism with a fast equilibrium first step and a slow second step. So if we look at another example, here we have 2NO2 plus F2 forming 2NO2 times F, 2NO2F, excuse me. And there's a proposed mechanism for this. So this is the overall chemical equation. Here's the proposed mechanism. In step 1, we have NO2 plus F2 forming NO2F plus F, and there's a slow step there. And then step 2 occurs much more quickly. We have NO2 plus F forms NO2F. We also are given experimental data. And what we're going to do with this experimental data is determine the rate law. We're going to do that one way. Okay, so that's our first way of determining the rate laws with experimental data. We saw this in our method of initial rates. Okay. We're also going to predict the rate law based on this proposed mechanism. And because our proposed mechanism has a slow first step, we can write the rate law based on this slow first step. So we'll have rate equals the rate constant K times NO2 times F2. Okay, so that's coming from the fact that we have a slow first step. This is an elementary reaction. From the elementary reaction, we can write the rate law. Okay, so this is predicted from the mechanism. Now, let's go back and recall how we do our method of initial rates. And let's determine the rate law based on that method. So if you recall, if we want to determine the order with respect to NO2, we're going to change the concentration of NO2 and hold the concentration of the other reactant F2 constant and see what happens to the rate. So our one method that we've described for doing this is to take, for NO2, we're going to take trial 1 and trial 3 and look at those rates. We're going to have the rate of 50 moles per liter per second over the 25 moles per liter per second. It's equal to the concentration for the third trial, 0.04, divided by 0.02. And we're going to figure out what we need to do in order to make both sides of this equation equal, solving for m. So we're going to have 2 equals 2 raised to the m, therefore m has to equal 1. For determining the order with respect to F2, we can look at trials 1 and 2. In those two trials, the concentration of NO2 is constant, but the concentration of F2 is changed. And again, looking at how the rate changes, so we'll have 75 moles per liter per second over 25 moles per liter per second is equal to 0.03 divided by 0.01 raised to some power, the order n. And so we'll have 3 equals 3 raised to the n, and therefore n must equal 1. So based on this, based on our initial rates problem, we'll get rate equals K times the concentration of NO2 raised to the order of 1 times the concentration of F2 raised to the order of 1. And so what we see from our predicted mechanism based on the slow step, we get the same rate law as what we get from experimental data. So these experimental data then are consistent with the proposed mechanism. So when we look at experimental data and compare that to a rate law, we can do one of two things. We can prove that the mechanism is incorrect, or we can prove that the mechanism is consistent with the rate law, or the rate law is consistent with the proposed mechanism. We are never able to prove that the mechanism is correct, okay? So that's never going to be a possibility. And in this case, we've shown that at least our proposed mechanism and the rate laws are consistent. Look at one more example. So here we're going to use some very generic reactants and products. We're going to look at 2P plus Q reacting to form 2R plus S. So this is the overall reaction. And what we're proposing is that this reaction occurs in 3 steps. In the first step, we have P plus P in equilibrium with T. This is a fast step, has equilibrium. We have a rate constant in the forward direction of K1, a rate constant in the reverse direction of K minus 1. For step 2, we're going to have the T that's produced in the first step combining with Q to form R plus U, and we'll have a rate constant of K2. Then in our third step, so our second step was the slow step. In our third step, we have another fast step, and we're going to have U produced in the second step reacting to form R plus S. So if we add up all of these equations, we're going to end up with our overall chemical equation, and you can verify that. So we are going to solve this problem just like we solved the other problem where we have a fast equilibrium first step and a slow second step. This third step in this case doesn't actually matter, okay? And so let's go ahead and write out what we expect, or do some math here to determine the rate law. So we're going to start again with our slow step. And based on the slow step, we can write a predicted rate law because this is an elementary reaction. Rate equals K2, that's the rate constant in the second chemical equation, times the concentration of T times the concentration of Q. But we know that T is an intermediate and it cannot show up in the rate law. So we need to write an equation that allows us to solve for T, and we can use equation 1 for that. So from equation 1, we're going to have rate in the forward direction equals K1 times the concentration of P squared. We're also going to have rate equals K minus 1 times the concentration of T. That's for the reverse reaction. Again, we have that equilibrium. The forward reaction and reverse reaction are happening simultaneously in a dynamic equilibrium. And importantly, the rates are equal. So because of that, we can set these two equations equal to each other. So I'll have K1 times P squared equals K minus 1 times T. And now we can solve for T. And we will get K1 over K minus 1 times P squared equals T. And now we can plug this into our rate law from step 2, okay? This equation here. So in doing that, we'll get rate equals K2 times K1 over K minus 1 times P squared times Q. And this is what our rate law would be predicted for this three-step reaction mechanism.